Hey everyone, my name is John, and today I want to go through the app I made, ElectronVisualized.org. It's going to be electronvisual.org. You can test it yourself, or you can download Atomizer AR on the Apple App Store. So first and foremost, I made this app in my grade 12 year because I thought the way they explain atomic orbitals and molecular orbitals in grade 12 chemistry was really not straightforward. It was very hard to imagine what these atom shapes are going to look like in real life. So that's why I kind of delved into finding better ways to visualize the atoms and molecular orbitals, the world of quantum mechanics in general. Let's explore the history of how I made this app. So now we're going to delve into the history of the app. So first and foremost, I basically started by making a demo website using React and React Native. Basically this page is the first version that I made in May 2022, and the only atomic orbital that is displayed is hydrogen. You can kind of see the circular shape of the 1s orbital. And this is plotted by SciPy and Matplotlib. Obviously hosted on Heroku. And this was the very first version that I made in terms of ElectronVisualized. I remember first committing this and being very surprised of how the plot is being plotted. So this is actually the calculations are running in the background live, instead of it just being an image. It's actually running in the background. So this is a project scope document that I wrote in May 2022. So I was kind of aiming this to students and teachers. And this was the mock-up sketch. We had different schedule milestones. And finally, last but not least, this is how I kind of planned out the tech stack. And the second iteration I made was basically plotting a hydrogen molecule. So I basically got two 1s orbital. The density is a little wrong here, but basically what I was trying to do is make a little molecular orbital diagram. This is sort of anti-bonding, but I was basically testing out the API using manual input, basically trying out the get and post request, and making the line diagram. And next up we got the little electron density going on, testing out the API. We're using DFT for molecular orbitals, and electron density for molecules. Then next up we got the full periodic table going on, and tested out on the iPad as well, as you can see. And then next up we got the full electron density plot going on. So even without the line diagram, you can kind of tell the structure of each atom, each molecule, and this is obviously all being plotted in the background live. And you can check it out later when you see the actual demo. So this specific depiction of the atomic electron density of a hydrogen molecule was actually featured on a scientific journal called it's actually a book made by David Clary at Oxford. So this professor actually reached out to me. He was a president of Magdalen College, Oxford, from 2005 to 2020. He was also Foreign and Commonwealth Office. He was the first chief scientific advisor at the British government between 2009 and 2013. So this professor actually reached out to me. So Sir David Clary. So he actually has a Sir in front of his name, but he actually has a little website here. Yeah, it's pretty cool, right? So it's called Walter Kahn. And this book is called DFT. So Walter Kahn is the godfather who made the DFT book. And I actually have his book as a paper copy right here. So as you can see, David Clary, the professor who reached out to me, he actually wrote a book like this. So I'm going to show you the exact email that I got from David Clary. Professor Sir David Clary. There we go. So he actually wrote me an email like this. And basically, this is the very book that he published. And as you can see, there's a diagram of the hydrogen molecule in the cover page. And there's an acknowledgement in its front page and personal acknowledgements. There is a section that mentions my name, which is going to be on this very page. I'm not sure if you can see it. So if you go on the World Scientific Journal, you can go to the preface and personal acknowledgements, and what you can see here is you can see my name right here on this page. So John Wonmusong, front cover credit. So that was pretty cool in my opinion. And yeah, and I guess I'll demo the website now. So first and foremost, this is the very website that I made. Obviously, there's a link to App Store and Google Play, just for your reference. There's a macOS version of this as well. It's called ElectronVisualized. It's on the App Store. If you search up ElectronVisualized, it's pretty apparent. It's right here. And you can see all the cool atoms and molecules. I think the desktop version is a little more fancy, so I'm gonna showcase that. So it's really the same website or the app, but you got atomic orbitals and molecular orbitals. And first and foremost, we're gonna explore the atomic orbitals here. This is the fanciest section of this very app. Let's have a look at, for example, palladium. Palladium is a really good example. You can see this really fancy animation going on. What you can see here is you can see that this is in fact a d orbital. There's a little structure in the middle and the outer structure at the ring and everything. If you look at the real life example of d orbital, and what they actually show you on the website is this diagram. So this diagram is a little less apparent. You can kind of tell that's sort of like electron cloud, but it's less apparent. It's just a shape. So this is the very depiction that I was trying to showcase here. But you can compare that each dot represent the probability of where the electron is going to be. And yeah, basically it's pretty cool. Let's probably have a look at another atom, which is gonna be cerium. Let's have a look at cerium. This is also a d orbital, but it's a slightly different kind of shape. So cerium is another really amazing example of an atomic orbital. Absolutely fancy. Have a look at that. So this is designed using SceneKit. And next up, let's try zinc. Let's try zinc. Zinc is also a really interesting example. You can see another configuration of a d orbital, and you can sort of compare it with the real life diagram, which is going to be dx2y2 orbital. Have a look at that. Absolutely fantastic. All right, now let's have a look at molecules. So there are a couple different molecules, and first and foremost, let's look at benzene. Benzene is a really interesting example because Yeah, there you go. So this is benzene, and you can kind of see that there's p orbitals. So this is actually a p orbital right here on the very right hand side. This is a p orbital, but this section actually displays p orbitals overlapping each other, which is just really really fancy. So you can see that the p orbitals here are overlapping, and you can see the molecular orbital diagram plotted also in real time. But you can also see the electron density here, all the way from ranging from 0 to 1. Pretty cool. This is where the atoms are, and you can kind of see the little bond between these atoms. Very cool. You can also set to anti-bonding. Anti-bonding sort of like separates these sections, and this is also very cool. So now these p orbitals are overlapping each other. It's called a pi bond, and these are the p orbitals. They're separate. And let's have a look at methanol. Methanol is also a really fancy example. So this is the anti-bonding configuration of methanol. Pretty cool. And let's have a look at the bonding position. Sort of like makes it all cohesive. So now all the orbitals are forming a overlap, and atomic orbitals combine and overlap to form a molecular orbital. So this is a very cool example right here. Very cool. I think this is definitely something that's really kind of visually, aesthetically pleasing, because it has so many different layers and structures. On the actual website, when you visualize this, what you can find out, for example, molecular hydrogen, shown in the example of David Clary's book, is this two H's bonding together to form a sigma bond. You can set it to anti-bonding, which basically separates these two s orbitals, and then they form like this two giant blobs. So this is anti-bonding. You can actually export this model, and what this is going to do is you can export the model into either JSON or GLTF. So if you actually export it as GLTF, what you can do is you can actually see the structure from a 3D modeling program. So for example, let's have a look at ethene. Ethene is another great example. So ethene has this bonding configuration and the anti-bonding configuration, which basically separates this pi bond into two different segments. So this is going to be p orbital and p orbital. P orbital, for instance, looks like this. So this is p orbital. So the one on the left is a s orbital, and the one on the right is a p orbital. And what I'm trying to showcase is p orbital to pi bond. So this is basically what I'm trying to showcase in this app. Two p orbitals overlapping each other to form a pi bond, which basically looks like this. This is a basic molecular orbital theory that you learn in the first year of university, or grade 12 year, or year 12 or something like that. Year 13, I think, in British high schools. But you can kind of see the bonding configuration and the anti-bonding configuration like that. And you can also export it as a 3D model just like that. And then you can open it from literally anywhere. Yeah, pretty cool. So you can actually view this on an Apple Vision Pro, which I actually made a project here. Three, two, one. The world is driven by thoughts. Thoughts that create something new, like artificial intelligence. But the common thing here is that it's all modeled after a So I actually made a little project.
I often think about the way you'll think about me when we're old.
So this is an actual
I always
operational
thought that
demo.
we could be the greatest story ever told.
You can see me wearing an Apple Vision Pro.
But there's a rock inside my sock, I'll keep on walking cause it's cold. And I can't stop the clock from ticking. I know that it's just the beginning. Don't forget.
So yeah, this is the demo that I made, and yeah, pretty cool stuff. Last but not least, we're gonna go through the ElectronVisual.org, the code that basically generates all the last but not least, we're going to go through all the code that generates this fancy molecular orbital and atomic orbital. That's going to be pretty simple, eh? So let's have a look at the production code. So it's going to be prod. And if you go on the code base, first of all, this little website is powered by Docker. It's containerized. And we're basically hosting both Python side and React side using one single Docker file. We're using Redis as well. We're using OpenBabel. It's handling all the job here. And it's using Firebase too. Yeah. So this is the React side of things. We have different components, states. We're using React. We're using Redux for state management. We have all the global variables here, including all the strings and everything. Tables, which is basically a periodic table. You can see all the code here. This is for the periodic table. As you can see, there's different elements here. Most important part is definitely the renderer, which is basically the 3D part of things, which uses the calls the API on the Python side to display all the atomic orbitals and the molecular orbitals. So we're using GLTFs for export, the standard web format, and we're calling the API here. This is the Python side of things. We're using get request. And we're basically getting, we're setting the global variable here using Redux. We're using Axios. And yeah, I think this is pretty cool. We're basically using, we're using a viewer. We're using instances actually for displaying all the points, because what happens often case is when you have so many points on the 3JS renderer, what happens is, oh my god. Yeah, so when you basically have so many points on the screen, just like how you would see in the copper example, when you have so many points like this on the screen, right? So first of all, these points are not 3D. These individual points are in 2D because it just consumes way too much RAM and way too much resources within this web browser. So I set them all to 2D, except for the iOS app example. The reason I show this demo is because even though it's the same, like it's using the same Python like API that I created, this one isn't actually in 3D. So these points are in 3D because it's less resource heavy. So for that reason, these points are in 3D. So in case of the iOS app example, what you can see is the points here are not in 2D, and the reason being is because it's much less resource heavy. Boom. So the reason being is this is much less resource heavy. So as you can see, these individual points are in 3D spheres. But in case of our web example, these individual points are in 2D. And the reason being is obviously because it's less resource heavy. So let's look at the same example, European. So these are slightly different. These are in 2D, right? Yeah, and basically this is the web component of this renderer. We're using full 32 buffer in order to store all these points. We're using instances, point geometry, and we're also using Redux. So this is basically, this is called instancing. It's basically attributing every single. This is a much more efficient way than just simply using for loop in order to copy and paste. We also have instances in 3D, which was a previous code that existed before we actually did 2D points. We got geometry for basically everything else. And you can check out the code yourself if you visit github.com. One more, ElectronVisualized. It's not synced up, it's not up to date per se with the fresh code base in ElectronVisual production version, but you can still get the idea of what's going on. If you go on client, source, and then components, you can see all the files here, as well as the server side, which contains all the code for atomic orbital, for example, which actually does contain all the calculations that were used to plot all these atomic orbitals. By the way, each time we generate this, it's gonna consume a lot of our power in our server. I'm using a small DigitalOcean server. I used to have no GPU, by the way. I actually don't have a GPU, so it's all CPU run, and I'm running like 10 other apps on it. So basically what it's doing is caching all this data into our S3 bucket. So we're using Amazon S3. So we're using AWS S3 bucket in order to cache all the data. This is probably the most complicated product that I ever made, Sign in. So, and we also got molecular orbital, which basically uses this library called PySCF and RDKit in order to create all these molecular orbitals using coefficients and everything, finding HOMO and LUMO, which is going to be the highest occupying molecular orbital and the lowest molecular orbital. We also got electron density, which does all the DFT calculations. So we're using DFT in order to calculate, and we're writing it to a file which we transfer to a client side, as you can see right there. Yeah, so we're using a AWS. Sign into a console. Root user email. DYGG43. Okay. I have so many different AWS accounts. And then I have to do multi-factor authentication. That's fine for me. Completely fine for me. Hello. Authenticator. 66. So if you go on S3 here, you can see that we have ElectronVisualized, and you can see all the cached stuff. You can go on benzene, and then you can also see download or open. You can see that it's gonna be like a JSON file. Oh my gosh. Okay. So it's like a JSON file that contains all the files here. You can see that everything's sort of like cached. It's like a massive file of like numbers, big numbers. And you can also see like different cached files. Yeah, so it's using S3 in order to cache all the files in order to efficiently render them. You can also see something like H2. H2 is another really nice example. We're gonna use, why is the pop-up window broken? Yeah, so you can see all these like different files, different numbers that are present. You can also see SPH, which represents all the atomic orbitals here. So you can see like all the numbers here. So these three numbers represent quantum numbers. So it's going to be n equals to 4, L equals to 3, and then M equals to 1. So if you ever heard of quantum numbers that you perhaps learned in chemistry, these are the quantum numbers. So these basically determine which atomic orbital shape it's going to be, and these numbers represent quantum numbers. So depending on that, you can kind of see what's going on. Oop. Sorry about that. Let's perhaps download it. View it on the big screen. And yeah, you can see here, right here, right? So it's going to be 431. So N number 4, L number 3. So normally it would be NLM. It's just in for reverse order for some reason. I don't know why. But you can see all the coordinates that are basically cached here. Right there. You could run this real time if you want, but it just takes like 30 seconds to generate because I'm just hosting so many other apps. Hosting this on DigitalOcean, by the way. Oh my god, I gotta log in instead. So this is what I'm using CapRover for the CLI, which is basically like Heroku, but it's like self-hosted. So you have to manually like set it up. But I'm using DigitalOcean. Oh my gosh, I gotta pay this off. Sorry. Oh my gosh, I gotta pay this off. My bad. But it's past due. But yeah, I'm basically using 32 gigs of RAM, but it's always, the memory is quite full, which is normal, but I'm basically hosting a bunch of different stuff here. Like we're running like a bunch of different apps. For example, Electron Visual. So we could basically see all the deployment logs here, the responses and everything, and errors. And we're also hosting like optically and everything. Like, so basically everything is running here. We also got the helper, which does all the smiles to IUPAC. So you can see that everything's kind of going through the server. And that's about it. Thanks for watching. And perhaps it'd be interesting to see the app actually running, which we can see that it's running on the phone as well. Atomic Orbital. Come on. There we go. Let's try Cobalt. Boom. So you can download this. You can check this out for yourself on the Apple App Store. You can see all the individual particles. Pretty cool. Pretty impressive, eh? Very cool, eh? You can see it for yourself. It's all available on Apple App Store. Then you can search up Atomizer AR. And then you're going to be able to see quantum visuals right there. And this is going to be the app. Has a couple of reviews, I guess. Beautiful app. It's okay. Yeah. So this is going to be the app. Yeah, thanks for watching. That's 2s orbital, by the way. Pretty cool, right? You can see the different, you can kind of see that there's 2 layers. So that's the first s orbital, and that's the parent s orbital. So it's gonna be pretty cool. Thanks for watching, guys.